Want to introduce the first speakers. Julia Scott and Scott Miremadi from the Brain and Memory Care Lab at Santa Clara University. They're going to be talking about study metrics of neuroimaging markers during virtual embodiment training for pain.
Hello, I'm Julia Scott, and I'm going to be starting the presentation and then passing it over to Soraya. And as you guys know, in a lab, the director may plan things, but the people who get it done are the students. So she's going to share the work that she's been leading over the last 9 months. Which way do I point? Sorry, it's not going forward. Is it on the big green button? I'm pressing the big green button. Oh. Okay, there we go. Okay. So we're looking at the clinical challenge of chronic pain. And chronic pain takes many different forms, and as we've seen in this conference, many different ways of treating it. But in terms of the scale of the challenge, in the US, as of 2021 metrics, we have 20% of adults living with chronic pain. And we've learned over the last decade or so that opioids and other pain medications are not a viable long-term solution, where the recommendations are now to have many different types of interventions, including non-pharmacological ones, to manage chronic pain, and a very specific recommendation from the CDC not to use opioids for chronic pain. So we're exploring what types of interventions can be used to change the cognitive processes behind chronic pain when the actual physical cause of the pain is past. So to do this, we need to look both at the psychology and at the neuroscience. I'm coming at this from the neuroscience perspective, and so I like the column on the left where you see lots of circuits. But what those circuits really manifest as is our psychological processes or cognitive processes of how we experience it. And with chronic pain, it's not just nociception. So if we're looking in the bottom corner of the circuits diagram, nociception, our perception of pain, but then there's the full experience of pain, which is affecting our cognition, it's affecting our emotions and attention and our memory. All of these things are interlinked. And so when we look at the column of cognitive or psychological processes, we can target any one of these. Likewise, which one of those you target should be reflected in what pathways are engaged in the intervention. So our focus right now is to look at one type of intervention called virtual embodiment therapy and investigate which of those circuits that we can detect through EEG are most related to this type of intervention. And just to review, embodiment is really looking at a use of imaging visualization techniques that transfer body ownership, their positioning, our proprioception, and our sense of agency and control over that visualization so that we can make use of proprioception and interoception. Okay. When we put these things together as a therapy, which we're going to use the abbreviation VET throughout the presentation, you have the ability to couple and decouple the visual feedback of the avatar. Right? This all stems from the inspiration of mirror box therapy with phantom limb pain. The limb is not there, the pain within the brain persists, and that can be unlearned or new memories formed by visualizing the movement of the limb as you expect it to be. When we transfer this into virtual reality, we can now have full control over what that visualization does. So you can have two arms and have the right arm control the left arm, the left leg control the right leg. And in that way, really work with our sense of perception to change our memory of pain. So the particular intervention that we're looking at, this virtual reality, VET, is playing with these two factors and making use of graded motor imagery to introduce new motions. So my main principle here is that the affected limb is being visualized by movements in the unaffected limb. so that you start forming a memory of normal functional movement in that arm or leg, that you have a hesitation or a fear memory of being able to move through its full functional range. This intervention is paired with mindfulness training throughout the physical activities. And that mindfulness training, the breathing exercises, is our contrast condition. Okay? And then there's coaching as well. And so I'm going to pass this over to Soraya.
Thank you. It's just this button right here.
Yeah. Mm-hmm. Oh, no.
No? Okay. Hi. Dr. Scott everyone can hear me, okay, good. Dr. Scott did an amazing job setting that up. I'm just going to talk a bit about our experimental design and what we were measuring in our experiments. So if we look at this flow chart here, what the main part of our experiment was this simultaneous collection of VR and EEG data, or kinematic data and the EEG data. So from the VR headset, we were able to look at smoothness of the right and left hand controllers, and that was our kinematic metric. Smoothness being an index of functional movement, and in a clinical setting, an index of functional recovery perhaps. And then for our EEG data, that was collected from this 24-channel EEG cap, and from that we calculated different spectral metrics that happen to be in the alpha frequency range from 8 to 12 hertz, but we'll talk about that more in just a second. But yeah, so the biggest thing was just this simultaneous acquisition of the EEG and VR data and what we could conclude from what we collected. So we had 10 participants. They didn't have any reported chronic pain or motor deficits, so 10 healthy adults, and they went through a series of activities in VR, and we used Karuna Home app, and you can select different activities, but the ones we selected were for upper body mobility, which could be reflected by smoothness of the right and left hands. But they went through a series of activities in a single session. They did have a trial session before, so they were used to the activities, and there would be less movement artifacts in terms of the EEG cap the second time around. But they go through these series of activities. They vary in terms of which arms you're using, whether there's mirroring involved, and that's when you see the opposite side of your body or your arm reflected in the avatar. And then our control condition for all of these were the breathing segments, and the breathing segments punctuated the series of activities. So you would do a motor task, and then breathing, motor task, breathing, and so on. And the exercises also varied in terms of complexity, so some were more complex than others. So these are our 4 candidate EEG metrics. We reviewed the literature. We found that these 4 were related to chronic pain in different ways, and they happen to fall in the alpha frequency range, which is just useful to remember. The first one was relative global alpha, so that's kind of measured across all of our electrodes. We have the layout on the right side to see. So we basically average the alpha power from all of those channels. In the literature, reduced global alpha power has been associated with higher chronic pain intensity. We had absolute frontal alpha, so that you would collect from the frontal electrodes. And then also frontal alpha asymmetry. We used electrodes F7 and 8 to do this calculation. And then peak alpha frequency. That one's pretty interesting because unlike these other ones that are more state markers, this one's a trait. So you can measure it at rest and predict someone's sensitivity to pain, whether that's chronic pain, acute pain. So that one was pretty cool. Okay, so this is our first slide of results. We found that relative global alpha, that first metric I just discussed, was significantly reduced in all of the VAT activities compared to the breathing segment. So we could say that this was modulated by the activity type. It actually decreased 40 to 50% from the breathing conditions, which is pretty significant. And then global or frontal alpha and alpha asymmetry, as well as peak alpha frequency, were not significantly modulated by activity, but we would like to, especially in regards to peak alpha frequency, we want to look at this with a larger sample size because we were limited by 10 people. They didn't have really varying levels of pain sensitivity, so that's something we could look at in the future perhaps. But the biggest thing from this slide is the relative global alpha showing sensitivity to the different activities. And then this is the smoothness slide. So as predicted, smoothness was a really sensitive metric for different activities in the virtual environment. We saw that more complex activities tended to display lower smoothness, which makes sense. And then smoothness was reduced in whatever arm you were using. And yeah, and we think that because it was able to detect varying motions and was sensitive to our different activities, that it could be a really useful metric moving forward with VET, and could represent any hesitations you might have when we're injured to moving. I'll give it back to Dr. Scott.
Thanks. Thank you, Soraya, for summarizing the findings from our healthy control study. And to put this in context about the relative global alpha, which is really the main takeaway that we have from the data so far, where we're working in this healthy population that does not have chronic pain, but they're doing virtual embodiment. And this measure that has been demonstrated to be related to pain sensitivity is being modulated by virtual embodiment. One of the things to keep in mind here is that alpha is that frequency range that's linked to a whole host of things in cognitive processes. And when we're looking at alpha over sensory motor regions, alpha suppression occurs during motor imagery. So what we think we're really picking up here with the relative global alpha is the cognitive process of virtual embodiment and the graded motor imagery, which makes it a sensitive thing to this type of intervention that you would unlikely see in something that is not embodied in terms of a CBT or other mindfulness applications. The mindfulness exercise here, you watch a flower bloom and close, and that guides your breathing. There's no representation of the avatar, and that's where we do not see this reduction in alpha. So this is telling us that we are picking up something sensitive to this type of intervention and the type of cognitive processes. In terms of the pain markers, we don't see variation because we have 22-year-olds doing this. Their peak alpha frequency is very low, but like Dr. Baker said yesterday, we're doing everything you shouldn't do while doing EEG. Some people are moving around, they're drawing in 3 dimensions, they're turning right, they're turning left, and we're getting quality data that we can measure for these types of metrics. So we have the confidence that as we move forward to work with a chronic pain group, and that would be our next steps, we can use these metrics as indicators of how someone may be responding to the therapy and figure out of those which is the most sensitive and may be useful in a clinical application when you're trying to get metrics of change in pain in addition to the self-report, something to corroborate or something to give a different insight or an indicator of what type of intervention is going to work for particular patients. Sorry, wrong one. Okay. So this work was led by Soraya in our lab in partnership with Lasya Maladi, who worked mostly on the kinematic data, while Soraya led on the EEG analysis, in partnership with Akshat Kalra. And both Lasya and Akshat are computer engineering students. In terms of developing the methods, we went to the literature and really looked at the work from the people who developed the metrics in the first place and went back to the source to make sure we're calculating everything correctly. So many thanks to all on the methods consultation side in terms of getting this to a point that we can be confident in what is represented here and it can move forward. Okay. Then there's all our references. Thank you. Any questions? Yeah, Walter?
Fantastic work, of course. I'm curious, you were describing this at your conclusion as a way to use a biomarker for chronic pain management. do you also envision using it dynamically during a experience that might be used to teach people chronic pain management, to give them feedback in real time during that experience?
So taking that metric of the virtual embodiment and then relaying it back within the user experience, I think that would be really great to see in one of the pain markers. And with that feedback to the person that you're making this improvement on this score, and making that a conscious connection with what's happening in the neural pathways.
How about maybe during a gameplay type of activity that might be distracting from acute pain, or perhaps, it doesn't sound like this is applicable to acute pain, but teaching somebody, not using the non-embodiment approaches, some other approaches, do you also think it could be useful there?
Wow, I hadn't thought that far ahead. It would, I think, in the sense that you create something that improves the engagement and the positive reinforcement with those biometrics is a fantastic way to get that adherence and reward processes in place, and to form these positive memories around the use of one's body when you're in this chronic state of inhibiting your movement, inhibiting your functional movement because of that history of pain.
Thank you. Thanks so much, Soraya and Julia.